Hello, welcome to the ECE seminar series and also the NYU CCS Hardware Security Seminar Series. It's my distinct pleasure to host Professor Chaoyan Yu from University of New Hampshire. She got her PhD from University of Rochester. She got an NSF Career Award in the area of hardware security, and she's one of the leading researchers in hardware security, and I look forward to hearing from her on this particular topic of 3D ICs and hardware security implications of 3D ICs.
Thank you, Ramesh. Thank you, Ramesh, for your nice introduction. So good morning, everyone. It is my pleasure to introduce my research project on the 3D hardware security. Great. In today's talk, I will discuss some of our research findings on the 3D dimensional integrated circuit and systems. Let's see, next slide. Industry have spent quite significant effort on pushing the chip manufacturing to the nanometer regions. If you can see that we have transferred 2 micrometer to like a few nanometers now. So we have hard time to keep pushing the technology scaling down to the physical limits of the silicon. So one way we can do is using structural enhancement techniques, try to keep the scaling. However, the vertical integration technology is one way for structural enhancement has different versions. For instance, we start from the package to package integration, then move to the interposer-based integration, which we consider as a 2.5D. So these two technologies essentially explore the feasibilities to connect dies with shorter global wires, so we can manage the delay better and as well as energy efficiency. However, these two technologies still suffer with very high capacitance and resistance. So through the silicon layer, as shown right here from Intel images, show that this is a true 3D architecture. However, the diameter for the vertical connection still in the few micrometer, which is much larger than the single die mental one connections. Monolithic 3D is a new 3D technology, which makes a via in the size with a few 50 nanometers around this area. So this is much closer to the M1 mental size we can use in 2D dies, which greatly reduce the global interconnect. All right. Although the 3D technology helped us to obtain tremendous benefits on the performance and energy efficiency, but the vertical connection integration of the multiple dies also bring in new and unexplored the security threats, including three-dimensional hardware Trojan, malicious TSVs, as well as a new way to leak information across multiple dies. A couple years ago, DARPA have a program supported splitting manufacturing. This is a nice technology to address the IP piracy issues on the two-dimensional chip. However, the split manufacturing cannot address malicious vertical communication. So this is a few examples to show how split manufacturing can help to make the system implementation incomplete from one die to another. So the attacker needs a complete knowledge for multiple dies. The split manufacturing does not help to address the security issues in the 3D technology itself. So in our research project, we try to address the security challenges in 3D IC from both attackers and defenders' perspectives. More specifically, we look into inter-die security, three-dimensional hardware Trojans, and also physical attacks in 3D ICs. So in the rest of my talk, I will address 4 things. One is, what is a new security vulnerability in 3D IC? What's the difference between the security threats we observed in 2D? And then we'll propose 3D Trojan model follow with the detection method for this specific 3D hardware Trojan. The fourth topic will be what does the power analysis attack look like in 3D ICs with special attention on the power distribution network. So the first one, we first want to compare that the security vulnerability in 3D is different than in the 2D. The primary reason of the new security threats in 3D is from the stacking structure based on the multiple dies, multiple 2D dies, and the vertical inter-die communication. Now we consider the information leak not only from one die. The information leak could happen through one die to the other because the security stress for each die will vary. So the information leak will be more sophisticated than the 2D scenarios. Unfortunately, the testing for the 3D circuits is not that mature yet. For example, when you have limited probe, it's not really realistic for you to check every single vertical connection channels at the same time. Plus, when we have much smaller dies, smaller feature size for each 2D dies, the probe we have currently, it could change the integrity of the TSV, for example, after testings. So there are limited testing ability available for us to perform very comprehensive testing on the 3D systems. So the potential risk, and actually also unique in the 3D IC, is now we need to consider malicious vertical connections and more hardware Trojans, which it has much more complicated trigger and payload architecture in the 3D system, as well as a cross-die information leak. So next one, I will revisit that for 3D circuits, what is new compared to 2D, other than the architecture level? So mainly that in the 3D architecture, the increased transistor density will challenge our intensive testing because now it's not very realistic for us to perform exhaustive functional testing. Oftentimes, we will perform testing on single die and vertical link separately. And after that, we'll apply some 3D level testing, but this testing will never reach the very 100% coverage. So if the attacker is crafted carefully at the system level, the limited 3D testing capabilities will limit us to really identify the very stealthy attacks on the 3D. In addition, the 3D integration will lead to larger process voltage and temperature variations. So this large variation will also lead to very high false positive rate if we using side channel signal to compare with normal behavior versus abnormal behaviors. So for example, if you're using delay-based testing as a side channel signals, you will see that in this multiple dimension or 3D dimension integrated circuits, the delay, critical delay, will have larger variations. Same thing for the temperature. You can see that if we only have one tier, the temperature variation is around 77 degrees. If you have more tiers, like 4 tiers right here, the temperature variation can change from 95 to like 101. So such larger processor variations will also cause another problem, which means if we increase the noise margin in our testing or functional verification, that relaxation will leave room for attacker to hide their attack effects. Let's use a thermal-based hardware Trojan as an example. So for example, right here, if the middle tier of the 3D stack have attacker exploited the temperature variation, try to create a voltage glitch. Now you see that because we usually relax the noise margin for the 3D compared to the 2D, and it's easier for attacker create some voltage glitch. That is called malfunction or the trigger signal for the hardware Trojan. So in addition to the thermal-based Trojan, 3D stacked Trojan architecture further cultivated cross-tier attacks, in which that the complete attack rely on the trigger signal from multiple types, or it's relying on the multiple tiers to contribute to the complete Trojan trigger and payload. On the right side, two pictures, it's showing that in one kind of hardware Trojan, you will see that the payload and the trigger are not all the same tier, or the trigger signals are distributed to the different tiers, so that the complete Trojan detection will be much more time consuming and also complicated than regular testing on the 2D cases. So we summarize that in the typical 3D fabrication process, we're showing it right here on the bottom. Besides the single die fabrications, we also have additional steps to implement the vertical connection and also the using bonding foundry to connect the multiple dies. So the extended fabrication steps will bring in new attack surface compared to the 2D fabrication case. We summarize the attack scenario in 3D in this table below and highlighted the untrusted stage. One thing I want to point out that in the foundry, now we split into two stages. One is a single die manufacture. This is similar in 2D. Another step will be vertical interconnect manufacture. So both two steps can be done in one foundry or separately. So we create 3 different trusted model here. Other than this, we will also see that now user will be another challenge because the user can consider as a single die user or the integration with multiple dies as well as a regular user for 3D chips. So overall, we'll consider this 4 different type attack scenarios when we design the hardware Trojan model, when we are looking into the side channel attack in later sections. So next section of my talk, I will introduce the characteristic for 3D hardware Trojan. Similar like 2D ICs, untrusted foundry could introduce hardware Trojan to 3D chips as well. So 3D Trojan can be triggered by many external signals. For example, thermal noise, rare event, or accelerated agent, electromagnetic interference. There are ad hoc Trojan examples reported in different literature. However, the comprehensive Trojan model for 3D circuits is still not clearly developed. So that's why we have one of our papers in publishing ISVSI. We distinguish different 3D hardware Trojan cases for hardware security community, so that we can develop different countermeasures aiming for different category. So in total, we have 4 models. We will explain case by case with examples. So in the first case, the Trojan trigger and the payload are in different tiers. P means payload, T means triggers. So only the Trojan payload is near the victim here. The trigger circuit is controlled by another tiers. This means that it's quite difficult to activate the Trojan when we do the single tier testing for the tier 2. The slides show here is one example of thermal triggered 3D Trojan for the case 1. So the Trojan trigger is a heat generator on the top tier. The Trojan payload is on bottom. In the second tier or middle tier right here, we have authentication unit. Usually we're well protected with different kind of other security primitives we designed for 2D. So in this cross-tier Trojans, it's implemented with very low cost, low hardware cost. Since the heat source is integrated in the 3D structure, typically the packaging level cooling systems usually happen on the top or the bottom will not help to adjust the heat dissipation from top tier to the middle tiers. So that if the attacker tries to leverage the heat distribution from top tier to middle tier, it will accelerate the Trojan triggering if we will control the heat generator in the top tiers. So if the 3D circuits have relaxed noise margin for the reliability for reliability purpose for other functional purpose. Then this relaxed noise margin or guard band on the temperature variation will lead the thermal triggered Trojan be undetected or will not have a high detect rate. To emulate the 3D thermal triggered Trojans, we using FPGA board and microcontroller as well as one temperature sensor connected as a whole system to demonstrate how the thermal triggered 3D Trojan will affect the trigger speed as well as the heat dissipation effect to the application we developed. For interested audience, you can watch our video links to see how the experiment implement. So in short, our demo illustrated that the thermal triggered the 3D Trojan could overwrite the password to an authentication system, which is protected in the middle tiers. The heat dissipation we emulated here is the top tiers. So we just look into how the stacked system will be affected if we trigger the thermal Trojans. So our toy circuits right here just to confirm that the heat triggered 3D Trojans is able to be activated with much faster speed than 2D if the input trigger input is appropriately controlled. In the second case, for the cross-tier Trojan payload. So compared to the first case, we swapped the payload and the trigger. That represent different scenarios from the attack. So in this case, you will see that the model could describe a covert channel implemented by cross-tier Trojan. When the trigger trigger condition is satisfied, the confidential information can leak through another tier, not the same tier. This is different than 2D because in 2D, usually the leaking will happen on the same tier. While you see in 3D, if one tier does not have an authentication system or some important informations, we normally reduce the security measures so that we can reduce the total cost. Now, if we have such different tiers integrated together, it is possible that the security information will leak through the weakly protected tiers. So this is a challenge, more challenging than the 2D case. One example we developed is the crypto key leak. So typically the crypto key will be saved or protected in valid memories, which is only accessible by authorized user. Now, if the cross-Trojan, as we described in the model, case 2 is in place, then the key could be modulated and transformed to other memory portions. So you see that we increase the multiple channels so that the key can be leaked from other way, not directly accessing the valid memory. That's why we can, this cross-tier Trojan will make it easier for attacker to implement the covert channel. We implement this case with two FPGA board and also assess how much hardware cost it could be if we implement covert channel by modulating the key and leak it through another lower protected memory. Actually, it's only increased LUT use by 1.3%. So it's a very low hardware cost. For that, we'll confirm that 3D hardware Trojan, it's easy to implement with very low cost. The covert channel could be another big challenge. The third one is another 3D Trojan. We call it multi-tie collaborative Trojan. What we mean by collaborative is the trigger signal will from multiple ties, not only from single ties. So this is a more advanced 3D Trojan than case 1, since the trigger Trojan can be controlled by 2 tiers, and the trigger mechanism can be a combination of temperature triggered, voltage triggered, or electromagnetic flux triggered. So if we have multiple tier integrated together as a 3D systems, there's very likely that attacker could using multiple trigger mechanisms to driving the Trojan in the tiers with the critical modules or important modules we want to protect it normally in 2D. So we implemented one interesting example with a multiple FPGA board. And again, we have a YouTube link provided for interested audience. You can watch how we performed. Overall, we want to emphasize that if you have a targeted module placed in the tier 3, other two tier 1, tier 2 are weakly protected. However, we can implement the Trojan triggers in other tiers, but the effect will go to the tier 3. So in this example, we try to using this 3D systems to do image authentication. For example, if the tier 3 will authenticate the input image from other tiers, whether match to the one is stored in the tier 3. If they match, then the application will move on. So the idea is if you have children in place in weakly protected tier 1 and the tier 2, and then the signal, invalid signal will pass to the tier 3. And then what's going to happen is the input data goes to tier 3 is already be interrupted by the Trojan triggered in the other tiers. The two pictures we show here is when the Trojan is triggered, you can see the Trojan can copy this. The Trojan will inject incorrect signal to the tier 3 so that it will affect the correlation on the image comparison. So what we confirmed with this emulation is if the 3D cross-tier multi-tier cooperative Trojan is triggered, then the authentication on the tier 3 is not only the hardware security challenge on the one tier problem, it have to come to the other portion of the entire systems. So the case 4, it is information leak in the passive tiers. So in this case, you will see that now the payload and the trigger circuit in the for the hardware Trojan all located in a single tier, but the victims will be located in the other tiers. This model actually represents snooping information across the tiers. This type of Trojan does not tamper the communication link and change the data integrity. Instead, it will assist to build a covert channel. We projected the case for Trojan will be more common in system level on design, such as a 3D network in Trojan. The picture I show right here is if you have information passed from bottom tier to top tier, rely on the communication infrastructure 3D NOC, you will see that a large IP calls could send NOC instruction to other layers, or you can leak information to different tiers. So this is a model showing that now if we integrate the multiple tiers with some existing on-chip communication infrastructure, we have to revisit how do we redesign those communication network properly. And if some of the module in the network has to be tampered, how do we address the hardware challenge, the hardware security challenge? In this example, we can see that one of the effects could be develop group if one of the routers in the communication network is altered by the attacker. Or we can see that information leak can happen. This is even simpler than the NOC routers. So with that, I will do a quick conclusion for this section, which means the main take-home message is vertical integration. Actually, it's enlarged the design space. The 3D design it challenge our design verification and integrity check. So we should be aware of the attack from other 3D tiers rather than a single tier where containing the critical information or the modules generate random numbers or the authentication modules. Obviously, it's not easy to do so. So I would think the community should look into how do we address system level attacks in the 3D system, which may be more complicated than 2D, because the trigger mechanism in 3D will be much more sophisticated than 2D, since we can have more combination of different triggering mechanism integrated together to multiple to the entire system. each tier may have carrying different kind of challenge, different security vulnerabilities. So this is a very imperative to develop our effective countermeasure to mitigating the multidimensional hardware Trojan. Next, I will introduce our investigation to how do we detect the Trojan in 3D IC. So recall that we know that the increase the PVT variation will challenge the 3D IC security. So we first perform the 3D Trojan detection in 3D ICs using the 2D approach to see what is the limitations. Okay, then we'll see how to improve it. The increase the PVT variation reduce the reliability of existing 2D Trojan detection method. That's our conclusion after the investigation. This is because that the detection method for 2D, they have to consider that the 3D ICs have larger variations. So we need to add more margins to tolerate the noise from other tiers. And otherwise, the Trojan detection method may have a very high false positive rate. If we try to balance the false positive rate versus the variations, then we'll see the 2D detection Trojan have some limitation in the 3D scenarios. Moreover, we could not heavily rely on the probes to perform hardware screening, since the probes are too big and there's not enough to place the probes on every single 3D vertical interconnect. So the testing also make the hardware defects detection harder. In addition to larger design space in the 3D will require us to develop more specific test vectors to recognize the cross-tier Trojan we projected before. This is challenging, especially for the 3D system, which will use the third-party IP cores. The signal pattern for those IP cores are typically not completely visible to the users. So it is not realistic that we can using test generator, for example, like a TetraMax, to produce a very comprehensive test bench for very high coverage testing. That's why the functional-based Trojan detection method is maybe not that effective as we do in the 2D. As an example, we examined a current signature-based 2D Trojan detection method in the 3D scenario. So the approach we used is a temporal self-referencing method, TSR method. This approach generates a constant transient current signature for the same set of state transition. So if there's no Trojan trigger, then signature will be stable whenever the state machine goes through same transition. However, if there's a Trojan in place, the current signature will be different if we collect different switching times. So this is a 2D approach we examined in the 3D scenario. The Trojan we implemented in our experiment is a Morris Trojan. This Morris Trojan basically modulated the key bit with a random number generator, and then the modulated results will charging the capacitor. So this is a 2D Trojan. Now we migrated to the 3D scenario by putting a random number generator and XOR in the tier 2, and the capacitor will be placed in tier 1, so that this modulated key bit can be leaked in a very, very stealthy way. Okay, so this is one result we got. We're using the point-wise Euclidean distance, try to see how this matrix will indicate whether there's a Trojan or not. The left picture is for the detection performed in the 2D. The orange bar are for the Trojan in case, and the blue bar is for the Trojan free case. So as you can see by this comparison, the Trojan in case always have higher Euclidean distance than the Trojan free case. So this is a good indication to show that TES approach is able to detect the 2D Trojans by looking into the current signature. The picture on the right shows the key results we performed in the 3D scenario. As you can see that the Euclidean distance for the children-free case now becomes slightly higher than the children-in case, which means if we're using TESR approach in our 3D scenarios, this testing approach will fail because there's more internal noise or processor variation going on in the 3D system. So the simply using TESR approach in the 3D scenarios will have very high false negative Trojans detection rate. So we already see that the time domain Trojan detection approach like TESR will fail in the 3D scenario. So we try to revisit it. How about we looking into the time domain side channel signal? How does the noise will be comparable with the Trojan indications on the signal current signal? So if you can see that we have Trojan-free case current transition over time, then we add 3 delta noise on top of the current. Then compare with the current signature from the Trojan-in case. You can see that there's only very few spots the Trojan will have higher transient current than the baseline or Trojan-free case plus 3 delta noise variation. So we try to simplify the picture as shown right here. Only those spots will indicate that it's abnormal on the current. The majority of the current signature will indicate that there's no Trojan. So this shows that the time domain side channel based Trojan detection approach will suffer from the 3D noise so that the Trojan detection rate will be reduced. All right, so because the Trojan detection approach in time domain is not that effective, so we switched to frequency domain analysis because we noticed that the frequency domain analysis is less sensitive to the 3D noise, so that the Trojan activities will be more obvious than in the frequency domain than the time domain. Right here, analysis. On the top equation is a model. We assume that if the current is contribute the primary signal, hardware Trojan in some noise, we're assuming that this primary signal is a sine wave. Then once we do Fourier transformation, what we're going to see is that it's very clear how does this affect the Trojan activity affect the frequency. The left picture shows that the Trojan activities may increase new clock frequency, new frequency spectrum shown here. The noise is quite low. And then next one, we will think if the noise is a Trojan does not contribute as additive noise, how about change it to the multiplicative noise? Then when we convert the signal to the frequency domain, now we will see that the primary signal will shift it. And this will cause us, say, if we compare the spectrum, then we can see that the Trojan will be able to detect it by checking the specific frequency signals. So because of that observation, we propose a frequency-based Trojan activity identification approach we call FTAI. So to perform the detection, what we need is a chip to perform the testing on chip level, collect the current. Then we using Fourier transformation to record the spectrum. Then we'll perform the same circuit at the transistor level as a reference. And we also will add the noise on top of processor variation noise to the transistor level reference. Then we'll do a comparison using matrix called the peak distance. So if you see on the right peak side, the peak distance we define as the abnormal frequency spectrum. We noticed that on the one side of the spectrum, then this distance will be a matrix to indicate whether there's a Trojan is in the circuit or not. So this is a one key simulation results we have. On the top pictures, it shows that we compare the peak distance matrix we come up with versus the Euclidean distance normally people use in the time domain comparison. You will see that peak distance matrix give us much higher difference between Trojan in and Trojan free case, like about 30 times or 40 times higher than Euclid distance. So because it's a matrix, we're able to increase our Trojan detection rate with less false positive. So you see on the left side, we perform the time domain Trojan detection based on the Euclidean distance. When we consider the processor variation in the simulation, we will see that there's two cases, especially for small Trojan size. You will see that those orange line for the small Trojan will have less Euclidean distance than the threshold, which is a baseline, does not have the processor variation. Now, for larger Trojan size, and yes, it can detect it, but for small Trojan size, then Euclidean distance is not sensitive enough to indicate there's a Trojan inside. Versus a frequency domain detection, we're using our peak distance as a matrix. Now you can see that all the Trojan size will have a higher peak distance than the threshold, which is the normal case without processor variation. So with that, we confirm that frequency domain seems more promising than time domain Trojan detection for the 3D scenario. Okay, so quick summary for this general 3D Trojan detection. We will say that 3D Trojan using frequency domain detection seems more reliable than the time domain because it can handle better noise and also interference with other random factors in the 3D case. So the last topic, I want to introduce the correlation power analysis attack in the 3D IC. So as we know that the CPA attack is more powerful than the SPA and DPA attack. So in this section that we'll introduce, how do we enhance the CPA resilience in the 3D IC? So in our work, we try to consider the 3D power distribution network, and it's composed of virtual VDD grid, global VDD grid, and some decoupling capacitance. And we will place the authentication module or encryption module in one of the plane and try to see the activities of other planes will affect the performance of the plane containing the encryption modules. So based on our theoretical analysis, we try to find out how does the noise, 3D noise, contribute to the correlation. So we first assume that the 3D noise is additive noise. By deriving the additive noise impact to the correlation coefficient, we notice that the correlation coefficient is proportional to the inversely proportional to the correlation coefficient. Now, this plot indicated that this correlation will reduce if we increase the variations. If the noise from 3D is multiplicative noise, then you will see that the correlation coefficient will proportion to these terms. That means if we have a ratio of a mu squared divided by the variance increase, then the correlation will increase. So this is theoretical analysis. We predicted if the noise from 3D structure is additive, this is how going to change the correlation. If it's multiplicative, then this is the trends. So with that in mind, we have the 3D models created in transistor level and try to measure how the power distributed network noise contributed to the middle layers signal. So we compare the power correlations. This is what we have if we have multiple tiers turned off, or one of the tiers turned off, or all of the tiers turned on. This is the power correlation we observed. And then we find out that if we turn off the plane 1 and plane 3, that will lead to the highest power correlation, which means the noise have least impact. And then we also have variance, power variance from each scenario, like a panel 1, plane 1, plane 3 off, or all planes on. So this is a correlation. This is a trend for the power variance. Now we compare the correlation coefficient and the variance. We notice that this is a relationship that matches to the theoretical analysis we did in the previous slides. is this one, which means the correlation will increase if we have less variance on the power noise. So that confirms that the 3D power noise is active, not multiplicative. Next one is, since we know the 3D power PDN noise is additive, then we are trying to see what is the other approach out there which can address the 3D noise in the CPU attacks. So many work you may find out is approach which is end-on modules, so that they will control the power distribution network, like do some regulations. So those kind of approaches nice, easy to use. However, one downside is the removal attack, because those extra modules implemented can be decoupled from the crypto modules. If that is the case, then those approach will not be that effective to address the CPU attacks in a 3D scenario. So what we proposed is try to develop some countermeasures which can integrate very well with the 3D design itself, so that attacker will have hard time to separate our countermeasure from the crypto modules we have in the 3D systems. So with that, we come up with two methods, spatially varied voltage and temporally varied supply voltage. What it means is, we know that in 3D we have variations on temperature or voltage. So why not do we take advantage of those small variations, use this as a source, noise source, which cannot be decoupled from design and will always be available for us to use in the real case. So we can either divide the crypto modules to sub-modules, and using the different supply voltage available in the 3D system, driving some modules separately. Or we take those supply voltages from different locations of the 3D system and drive the crypto module as a whole with dynamic rotation fashion, so that the crypto module will be driven by different voltage at different time. So let's zoom in to see how the spatially varied supply voltage look like. If we look at a transient simulation, you will see that the local VDD voltage will vary with different variance. So this is the variance we want to leverage to drive the crypto modules. Because of this, that the power traces we collect from our method will be different than the theoretical prediction for the power consumption were generated by the crypto module. So this is a correlation coefficient we obtained from the Triple Whisper analyzer. So as we showed here, for the baseline, you will see the critical key has a higher correlation coefficient than the wrong keys. That means in the baseline, we are able to retrieve the key bit. Now, once we apply our proposed method, which take advantage of multiple supply voltage driven in the crypto modules, then you see that the correlation for the correct key will be lower than the wrong key. So the key will not be even retrieved after the 200 power traces. We're also using the guessing entropy as another matrix to see how fast the key can be retrieved if we have more power traces. So from right picture, you can see that the baseline, which using the single VDD, you will see that you can retrieve almost all the subkeys with 1,000 power traces. And for our approaches, we slow down the key retrieval speed. With more power traces, maybe eventually can be retrieved, but at least our approach will make the CPU attack key retrieval with a lower speed. Another experiment we did is, let's see how the key bit has been retrieved by applying different supply voltages. So you see that if we using different supply voltage generate more power traces, we perform the experiment, we see that with 8,000 power traces, you see our proposed method still cannot completely retrieve will not leak the key completely, because there's 3 subkeys still not reached to the threshold that will indicate the subkey is retrieved. Now, if you look at the number of subkeys retrieved by the power traces, for 8,000 power traces, we still did not reach to the 100% key retrieval. And versus the baseline one, it will already retrieve the key with early number of power traces. A more interesting experiment we did is, we know that different supply voltage will contribute to power trace differently. So we try to spend try to use the supply voltage with different percentage of the power traces contribute to the entire CPU analysis. For instance, in this case, we have more driven voltage on the 1.25 volts. In this case, we have more voltage applied 1.1 volts. And we have power traces collected with different combination of the power traces and analyze it, how the key retrieval speed look like. For the baseline, which using one supply voltage at the normal voltage level, the other combinations with 4 different supply voltage. So you see that the mixed supply voltage will lead to a slower key retrieval speed, even with 8,000 power traces. We understand that if we apply countermeasures to address one attack, we have to consider the countermeasure itself may leak information. That's why we performed a test vector leakage assessment, TVSA approach, to see that whether our countermeasure will leak some new information. So our conclusion is no, because the baseline will have 4.9 TVSI. Our method only have 3.7. That means the proposed method does not leak does not contribute to leak the key, since the cutoff point for TVS indicate whether the correlation between the countermeasures on the CPA resilience versus key retrieval is 4.5. So we are still way below the threshold. With that, I want to conclude the CPA attack in the 3D. We want to say that it is very critical for us to develop some countermeasures cannot be easily removed from the design. The highly coupled the countermeasure in the 3D design will be a good way to address the CPA or side channel attacks in the 3D systems. The overall in this talk, I have discussed that 3D ICs have some new features in security vulnerability, and really the community should revisit that. Maybe the 2D hardware Trojan approach, detection approach may not be efficient to detect 3D Trojan. We should design some countermeasures specifically designed for 3D scenarios and do some investigation beyond the traditional split manufacturing approach. Importantly, that I think the inter-die security and die-to-die authentication should be investigated in the future. To either we can use the architecture level approach to develop some countermeasures, or have something totally new to address the hardware tampering or side channel leakage issues in the 3D scenario. Okay, with that, I would really appreciate the NSF and the SRC supported this project. And we also have a collaboration with Dr. Emery Selman in Stony Brook. 3 students contributed to this project. They have done enough work for this project to make create some important results for me. I really appreciate their contribution. With that, conclude the talk. I will be happy to take questions. Thank you.
Thank you, Chavian. Excellent talk. Any questions for Professor Chavian Yu? I have one question to lead off. One is how do the results that you show on your FPGA setup translate into the 3D stack and so on?
Yes, thank you. This is a very good question. Actually, we have this similar question in the past. So the one limitation, actually one challenge for us to perform 3D experiment is a real 3D chip. So we try to using the FPGA to emulate at least function-wise to see how the signal can be from one tier pass to another tier, how the combination of the functional attack will happen in the 3D scenario. So again, this FPGA emulation does not verify the performance in the 3D case, but at least we can confirm how the triggering mechanism can propagate to one one tier to another tier. It's just a functional verification, not a performance assessment.
Okay. Have you looked into, so maybe Johan is on the call. Johan, do you have any question in terms of how you approach this issue? Johan Nektel is from NYU Abu Dhabi, so I'm just calling him, see if he has any thoughts or questions on this, if he's there. Let's see if he's, I don't know if he's.
Yeah.
Oh,
yeah,
we have a couple of, Animesh has a question. How robust is the Euclidean distance measure to detect Trojan from noise versus process variation? Slide 42, 43.
Okay, let me see, 42 to 43. 2 to 43. So I can share again. I can share the screen here. This one, right? Yeah. So this is we're using Euclidean distance, and right here when we repeat when we perform the simulation, we repeat the experiment many times, try to confirm that this is the stabilized results. So overall, our conclusion is if the processor variation is considered in using the Euclidean distance, the matrix have very minor difference. They have very small difference compared to the threshold. It's very easy to guess lead to the false negative detection rate in the time domain analysis.
One more question at the end. You showed that you were able to leak most of the keys, right?
In the last section, right?
Yeah.
Last section. Let me see. This one?
Yes, they at some point you were able to leak most of the keys. The rest is you could potentially guess them. You don't need all the bits, right?
Yes. So the point we want to make is if we consider do the comparison, we will see that our countermeasures does not thwart the CPU attack completely. Just slow down the CPU attacks, the key retrieval speed. That is the point to make. I mean, now when you slow down, you can see that this is only for the experiment 1S box. Mm-hmm. If you consider that you have multiple bits to retrieve all the subkeys for one AES, then it will take a much more power traces. So when you slow down the CPU attack success speed, it still makes sense, although it's not completely thwarted. Because our experiment, yeah.
Yeah. Thank you. Johan, were you saying something? So thanks for the talk. Yeah, I agree. Evaluation on real 3D hardware would be important, but not easy to do as of now. And mm-hmm. Question, which technology, and this is a question from Johan, which 3D technology, TSV versus monolithic versus interposer, do you feel offers most promise for improving security, and which technology would lead to most risk?
I would think the TSV one, because, oh no, wait, I take it back, interposer one. So in general, my feeling is if the fabrication steps, especially in the vertical connection side, if you make the vertical connection foundries easy to access your designs, then lead to more risk. For monolithic 3D, actually we had some work on monolithic 3D securities. Basically for that, it's lower risk. The reason is now the whole foundries will do the vertical connection via MIV and the die fabrication at once. Also multiple steps, but it will be done in one foundry. So the threat model will be different than what I presented in the 4 cases. In the 4 Trojan model, we show that we're assuming the foundry, one foundry do the die testing, die fabrication, another foundry do the via fabrication or alignment. So there's multiple foundries working together. Then it takes more steps to prevent the information leak. Basically, there's more attack surface. So in general, I feel like a monolithic 3D will be less risky than other TSV and interposer. That's my general feeling. Yeah.
Thank you. In terms of, I have on the platform that you use for this particular project, for this particular phase, power side channel, trace collection, and so on. What's this Whisperer board? Can you, is this a board that's available in the, that you developed, or where is, you talk about Whisperer?
Okay, so I can choose this one. So we have two platforms. One is we using transistor level implementation. We basically implement the power distributed network in the transistor level. And also we have a PDN network, which is created by my collaborator, Emery Selman. We implement the logical function in each tiers. So the whole simulation is performed in transistor level. That's why we can fully control all the power noises, all the noise from 3D to another one. Then we also can decide which one want to mutate using decoupling techniques or not. So in our early GLSVSI papers, we discussed this experiment setup. Then we using the Chip Whisper as a software try to analyze the signal correlations, or we later on we also develop a MATLAB platform to analyze all the power traces that were collected for the transistor level simulation. Overall, I would say this kind of analyze to see whether PD is additive noise or multiplicative noise is meaningful, so that it will direct us to design proper countermeasures. So which way will be effective? Power voltage one is one kind. I do believe there's many others way. How can we using the additive features to design the countermeasure, which will be effective to thwart the CPU attack in the 3D scenario. It is a very time consuming, I have to admit, for transistor level simulation, but it gives us more flexibility to investigate how the decoupling techniques used in 3D affect the countermeasures that we designed for the CPA resilience.
Any other questions from the audience?
Another thing I would share is we also try to get 3D FPGAs to perform more realistic performance wide kind of evaluation. We really tried, but currently the 3D FPGA board mainly is not like a stacked like what we want to have as a TSV based stack. Mainly they just have a memory layers on the one layer and the function on the bottom. So existing 3D FPGA really does not, I do not find the best FPGA board available, but I wish maybe someday FPGA could FPGA company could produce some really 3D stacked FPGA for us to use. Interposer wise, yes, we can do, but it's not like a vertical communication. So the noise dissipation or heat dissipation from one tier to another tier, we couldn't find a good platform to perform our simulation or perform our emulation. So that's why we mainly rely on the transistor level simulation with practical PDN models in Cadence. So that's how we did it.
Okay. Thank you for that talk about this new direction in hardware security, an increasingly important direction, I think. Hardware, the 3D, especially with the various options that you outlined, interposer versus monolithic versus TSV. On that note, if others do not have any questions, please join me in thanking Professor Chavian Yu for this excellent presentation. And Chavian, I owe you where once the country opens up post-pandemic, I will invite you to visit us again. And thank you so much.
Thank you, Ramesh, for inviting me. Thank you, everyone. Feel free to reach me if you have further questions. Thank you.
Thank you.
Hi, Raquel.